Well, hi everyone. My name is Santiago Arango-Piñeros. Before I start, I would like to thank the organizers of the Connecticut Summer School in Number Theory for sharing this video with you. Today I'm going to talk about the Euler function of a global field, and well, this is all joint work with my friend Juan Diego Rojas. Let me start with the classics. So the Euler function is defined, phi of n is the size of the group of units mod n. It is also the number of positive integers not exceeding n, which are relatively prime to n. And the Chinese remainder theorem and the fact that taking unit behaves well with respect to finite products implies that phi is a multiplicative function, meaning that if I have a and b relatively prime, then phi of ab is the same as phi of a times phi of b. Moreover, if I have a prime power, then the ring of integers mod p to the r is a local ring, meaning that it has a unique maximal ideal. And this maximal ideal is the ideal generated by p. This allows one to calculate the number of units as the number of elements outside the maximal ideal. So this gives that phi of p to the r is going to be p to the r, the size of the whole ring, minus p to the r minus 1, the size of the maximal ideal. And, well, if you have the factorization into prime powers of your integer n, then you have an expression for phi in terms of that factorization. And this is called, I'm going to refer to this as the product formula. Okay, and this product formula is extremely important for, many results in analytic number theory. Cool curiosity that stems from the product formula is an explanation for these straight lines arising in the graph of phi of n. So let's take one of these lines, and let's say, for instance, that the equation of this line is y equals m times x. It's a straight line going through the origin. Then, if I fix a finite set of primes, so let S be a finite set of primes, say from P1 up to Pm, then this slope is going to be, for some fixed set of primes, is going to be the term in the product formula with primes exactly in S. So this is an interesting curiosity. On a more serious note, define T of n to be the totient multiplicity of the integer n. That is the size of the fiber of n via phi. Right? So a very nice theorem of Erdős, Dressler, and Bateman is that, if I denote by zeta the Riemann zeta function, then the mean value of this totient multiplicity is going to be zeta of 2 times zeta of 3 over zeta of 6. And just as a foreshadowing, let me write number 1 here. Let me just explain what the idea of the proof is. I'm gonna mostly focus on explaining the results. Most of the proofs in the global field case are gonna be very similar. So Each one of these authors gave a different proof. The proof of Bateman was essentially analytic, so he considers the Dirichlet series associated with the Euler function. So he considers a function T of S equal to this sum. He shows that this series converges absolutely on the right half plane real part of S greater than 1. And using absolute convergence, he rearranges the sum to obtain the totient multiplicity as a coefficient of the Dirichlet series. He then shows that T has a simple pole at S equals 1. And he's able to calculate this residue, which gives exactly Z of 2 times Z of 3 over Z of 6. And, well, he then uses a Tauberian theorem, the Wiener-Ikehara theorem, which basically says that if you have a Dirichlet series with simple pole, with domain of convergence real part of S greater than 1 and a simple pole at S equals 1, then the mean value of the terms in the Dirichlet series is going to be the residue of the Dirichlet series at S equals 1. So the idea is mainly understanding the analytical properties of the associated zeta function. So after the summer school, you're probably all experts in global fields. Let me just say some things to fix notation. So I'm going to denote by K a global field. So this is either a number field or a function field. So a finite extension of FQT. By X, I'm going to mean the associated scheme. So X in the number field case is going to be the prime spectrum of OK, the ring of integers. And in the function field case, X is going to be the smooth projective curve with field of functions isomorphic to K. I'm going to denote by P. In the number field case, P is going to be a maximal ideal or a closed point of X, the prime spectrum. So maximal ideal. In the function field case, P is going to denote a closed point. By D plus of X, I mean the effective weight visors. So in the number field case, if you don't know what that is, you can just think that an element of D plus of X is going to be a non-zero integral ideal, right? So I have a prime factorization into prime ideals, into maximal ideals, given by the Dedekind condition. And, well, an effective divisor in general is just a formal sum of closed points where the coefficients are positive, well, non-negative. Right? By OP, I'm going to mean, well, in the number field case, this is going to be the localization of the ring of integers at the maximal ideal P. In the function field case, this is going to be the stock at P, so the meromorphic functions, which are regular at P if you want. And P is the maximal ideal of OP, so OP is always a local ring. And the maximal ideal is going to be denoted by MP. In the number field case, this is the ideal generated by P. By KP, I mean the residue field, so this is isomorphic to OK mod P in the number field case. And, well, the degree first of a point is the dimension of a closed point is the dimension of the residue field as an FP vector space, where small p is a rational prime lying under uppercase P. And well, in the function field case, this is the same, the vector space, FQ vector space, that dimension of the residue field. So this is the degree. And K is going to be the norm. So this is the size of the finite ring OK mod I, where I is an ideal. And in the function field case, this is Q to the degree of P. So maybe I should mention that you extend the definition of the degree for arbitrary divisors by linearity. And well, here, this doesn't have to be a P, but a general divisor. Great. So now that we have fixed some notation, we can dive into our results. The first thing we did was give a new perspective on the norm of a global field, and we did it like this. So pick an effective divisor D and define OD to be the ring given by the intersection of the stocks over all primes in the support of D. So this is OD, and ID is going to be the intersection of all the maximal ideals. So it's not very hard to see that ID is an ideal in OD. And well, recall that two effective divisors are called coprime, basically if they don't have any prime powers in common, right? So if they supports have empty intersection. So the first result we have, which is a simple lemma in commutative algebra, but turns out to be very important for the applications, is that if I have two relatively prime effective divisors A and B, then we have this ring isomorphism. So this result is reminiscent of the Chinese remainder theorem, but it's not exactly the Chinese remainder theorem. We weren't able to find proof of this in any commutative algebra books or articles, so we gave a proof in our paper. It's pretty straightforward. And with this in place, we define the norm of K to be the size of this finite ring. So this is going to be the norm. And by analogy, in the case of the integers, we define the Euler function as the size of the units of this ring. So an interesting fact is that maybe the first definition, the one that you would probably have guessed, was to count effective divisors with norm less than D, which are relatively prime to D. But this doesn't work in the case of P1, for instance. So for number fields, the counting property definition works. It coincides with this definition of the Euler function, but in the function field case, it's not true. And well, the nice thing about this definition is that the expected properties of the Euler function follow easily. So, for instance, we recovered the product formula. This follows essentially from the previous lemma. So we have the product formula. And once we have the product formula, well, everything else follows pretty easily. So as Bateman, we consider the associated zeta functions. So the Dedekind-Weil zeta function of k is the zeta function associated to the norm. And we consider the totient zeta function, or the Bateman zeta function, which is the zeta function associated to the Euler function. And we prove some analytical properties of this function following the results of Bateman. So if we denote by TKS the zeta function, the totient zeta function, then we prove that this series converges absolutely and uniformly on the half-plane real part of s greater than 1. And furthermore, we can factor out the zeta function. So this is going to be some function f times the Dedekind-Weil zeta function of the global field. And f of k is given by this Euler product. So the product over all closed points of this expression over here. Well, once we have this, we furthermore show that this function f, this Euler product, is holomorphic on the real part of s greater than 0. And since we can factor t as f times zeta, this implies that t has a unique simple pole with real part, in the closed half plane real part of s greater than 1, with residue f of 1 times the residue of the zeta function, right? So this is the residue of t at s equals 1. And an honest calculation gives that f of 1 is zeta of 2 times zeta of 3 over zeta of 6. And applying once again the Tauberian theorem of Wiener and Aikahara, then we recover the theorem of Erdős, Dressler, and Bateman, with the difference that we have now the residue of the zeta function, which in the case of the rational numbers was just 1. So, this is basically it. If you are interested in looking closer at these results, then you can look out our paper, which is in the archive. Please feel free to reach out and ask questions if you have any. So the paper is on the archive. And thank you very much for watching this video.